Yeah, so this week we're talking about rocketry and orbital mechanics. And we're going to demo some things with Kerbal Space Program. We figured it might be a cool visual aid and fun interactive activity that all of you could participate in and give us feedback and help do different simulations and things like that. So first off, please sign in, as always. Leave it up for a little bit so you can scan the QR code. Maybe one of the other eBoard members can drop the link in the Zoom chat as well. So we'll leave that up for a little bit. All right, we'll just move on. Once again, we have a Discord server now. So if you aren't aware, Discord is just a place where we as a club can further communicate outside of Stony Brook online. We have different channels for talking about like space news, memes, general club announcements. It's just another way for us to interact with you and for you all to interact with each other. So I'll leave that up if any of you are interested in that for a few seconds. Okay, and moving on to some space news, a few things have been happening since we last met. Eyal, if you want to talk about the super pink moon.
Oh yeah, sorry. I was trying to think of an answer for the question of the day.
Okay.
I'll have to keep thinking. Okay, so a couple nights ago was a supermoon, specifically a pink supermoon or super pink moon. And so Alex was actually asking me about this yesterday. You can see in the picture, the moon's got a bit of a funky color. And that's actually got nothing to do with why this was a pink moon. So pink moon was really just the name for like the moon, the full moon of this month. So every month the full moon has a different name according to basically like old Native American lore. And so one of the moons is this full moon was the pink moon. There's others that are like the wolf moon, the beaver moon. We've talked about this a little bit before. Blue moon is another one of them. So if you've heard people say once in a blue moon, it doesn't, it kind of comes from that. And basically that means once a year, even though that's probably not what they really mean. So that's what the pink moon was, had nothing to do with its actual color. And supermoon, a lot of you probably already know, is because the moon at this point was at its closest in its orbit around the Earth. So the moon's orbit around the Earth isn't perfectly circular. At some points it's a little closer, sometimes it's a little further away. And that doesn't perfectly line up with when it's a full moon either. So some full moons are bigger than others. So why does the moon actually have these funky colors? Well, that's actually specifically when it's low in the sky. So when the moon is high in the sky, regardless of whether we're calling it a pink moon or not, it's going to look, just kind of like bright and white or gray or silver, whatever you want to call it. But when it's low in the sky, if you take a look at the little diagram I've got to the bottom right of the screen, the light from the moon is actually passing through more atmosphere than when it's up high. So in the diagram, it actually says the sun, and that's because it's the same effect when you have the sunset. So when the sun is high in the sky, it just looks like really kind of pale or yellow maybe. But when it's low in the sky during sunset or sunrise, it looks red, and that's because the light is passing through more atmosphere, and the effect that the atmosphere has is that it scatters blue light around more. And so the only light that's reaching us directly is the more redder tones. And that's the same thing that's happening with the moon. All right.
All right, on to some moon mining. So on April 6th, President Trump signed an executive order called the Order on Encouraging International Support for the Recovery and Use of Space Resources. The order basically said that the US would like to mine resources from non-Earth objects, mainly the moon and asteroids, and use those for scientific and non-scientific resources. It basically states that the moon is not going to be known as like a global commons, so it kind of goes in line with how in 1979 a moon treaty was proposed that said that any spacefaring nation, whatever resources from the moon they would use, if it's a non-scientific use, they would have to be under the regulation of international law, and most major spacefaring countries did not sign it, including the US. So the new executive order that Trump signed kind of follows in line with that, where the US will not go in line with international restrictions based upon different mining options and different uses of space resources. And it is in a way a clarification of how the US would like to address further international partnerships. Basically, the Artemis program will be a mostly US-based effort, but they would like international partners, but they want to kind of define how the partnership would work and the fact that they will use different resources from the moon for non-scientific purposes as well.
So before we get into the bulk of the presentation, we just have, I think, one announcement. So thank you to those of you who emailed us saying that you were interested in running for an e-board position. We will be holding our elections 2 weeks from today on April 23rd during our normal GBM time. So what we will do for that, each candidate who's running will give a short speech, probably around 2 minutes. They can have visuals as well if they'd like. There will also be time for questions and answers for each of them. And all of that will be recorded. And so after the meeting, all the voting will be done on a Google form. So we will be sending that out to our members, and that will be open for members to vote for a week. So we'll also attach the recordings of each candidate for each position so that people can also see the speeches and their question and answer portion. This way we want to make sure that we get the most interaction from our members, whether they can make the meetings or not, and still have a deciding voice in who's on the e-board next year. So we will be confirming over the next week who actually decided to run. So in next week's email, we'll announce who the candidates are for the position. And in that time, we will just confirm with them and give them time to prepare their speeches and all that. Does anyone have any questions about how elections will work? Okay then, so we'll get right into the presentation then. If you have any questions, feel free to ask them in the chat, email us later, anything like that. So rocketry and orbital dynamic mechanics with Kerbal Space Program.
All right, so rockets, where did they come from? Where did they go? Cotton Eye Joe. The first rockets were probably developed by the Chinese in the early 1200s. And so initially, they probably came from things like fireworks, actually, which were supposed to, like, you know, explode in pretty colors. And maybe at some point, something didn't quite explode and just went flying. And people were like, hey, maybe we can use this for other purposes. And so they were used for things like battle. A bamboo tube could be filled with gunpowder and attached to an arrow. And then that could be lit. And the gas produced by the burning gunpowder would escape from an opening, and that would propel the arrow. Eventually, so those arrows were still shot from bows, actually, and then eventually it was found that, you know, they could just launch themselves. You don't have to launch them from a bow. And so in the bottom right picture, you see this guy in this lovely cartoon lighting one of these bamboo rockets filled with gunpowder, and that the long stick actually is a sort of guiding mechanism. So that keeps the what was called a fire arrow on course rather than just kind of like flying in whatever direction, which could be very dangerous because these things were about as prone to just explode in your face as they were to actually propel effectively. The actual effectiveness of this in battle is questionable, but it had like the added bonus of causing psychological distress in your enemies, because if you're getting barraged by a bunch of like fire arrows, that's pretty frightening, you know, rather than just regular arrows. So even if they might not have been super effective, it would still be pretty terrifying to be faced by that. So China actually did use that against Mongolia in defense, and then I think the Mongols at one point started developing their own rockets, and it spread to Europe eventually. Italians at one point designed torpedoes powered by these rockets, like surface torpedoes. Pretty wild stuff. All right. Next slide. Initially rockets were powered by gunpowder, which is solid, so that would be a solid propellant. But it was later found that liquid propellant might be more effective at allowing a rocket to fly further, faster, higher, things like that. And so that idea was developed by a Russian school teacher in 1903 in a paper that he published in 1903. He discussed the possibility of using liquid propellant. So that could be like gasoline, for example. But the task of using liquid propellant is actually much more difficult than solid propellant, because the whole mechanism requires a lot of other aspects to it, like oxygen tanks and ventilation, various things like that. There's this fun, complicated diagram that I have here just to show that it is more complex than having a tube filled with gunpowder that you can light. So the idea was developed by this Russian guy, but finally the practical aspect of it was developed by Goddard, who in the 1900s was testing various propellants, very solid propellants such as gunpowder, and then finally tried out liquid propellants. And he was really the first successful person in having liquid propellants. So Gabriel points out that you also have to pump fuel/oxidizer into the engine against the pressure of the reaction with liquid propellants. So yeah, much more complicated than solid propellant. Thanks for that point. All right.
I think it's skipping a slide in between there. Can you go back real quick, Alex? Thanks. Yeah, so then into sort of the modern era of rockets, what we think of as, you know, space rockets. They're mostly combinations of those two types of rockets, either solid fuel or liquid booster or both. So the V2 was the first long-range guided ballistic missile, and a missile is basically just a rocket with a bomb on top instead of people. So that was built by Germany during World War II by Werner von Braun. It was powered by a liquid fuel engine. And then next we go to the Vostok, which was a Soviet rocket built during the Cold War space race. Also liquid fuel. It was a multi-stage rocket, which means that the rocket separated into multiple pieces after launching rather than staying all together. And that put the first human, Yuri Gagarin, into space in 1961. And then moving on to American rockets, the Saturn rockets, also worked done by Werner von Braun after we convinced him to come here once we won World War II against Germany. We stole a bunch of their scientists and got them to come build rockets for us instead. And the Saturn rockets were the ones that launched the Apollo missions, including the first moon landing, Apollo 11. And then one of the more complicated rocket systems that we have ever built was the space shuttle, which was a combination of liquid fuel and solid fuel rockets. So when you look at the shuttle itself, which is sort of that plane-like body on the front there, the shuttle has its own thrusters, which are liquid fuel rockets. And then that big orange booster in the back is also a liquid fuel rocket. But those two white boosters on the side are solid rocket boosters, or SRBs for short. So the shuttle would launch with all of those active, all the liquid fuel and solid rocket boosters at the same time. And then the SRBs, the solid rocket boosters, would detach first before it got into orbit. And then by the time it got into orbit, the main booster, that liquid fuel one that's orange in the back, would also detach, and you'd be left with just the shuttle in orbit. And it could perform its own orbital maneuvers with its liquid fuel engines, and then it could slow down its orbit to return back to Earth with its engines as well. And then a big difference between the space shuttle and other rockets is that the space shuttle would enter the atmosphere, and then it would use its wings to generate enough lift that it could land sort of like a plane. It didn't quite have a very good aerodynamic design. I know that one of the astronauts that flew the space shuttle said it was like trying to land a brick with wings. So it wasn't quite as nice as flying a plane, but it was able to land well enough that it could be reused. So instead of separating into a bunch of small pieces and just returning the very top part with parachutes, the space shuttle could sort of glide down and slow itself down enough with the lift from its wings that it could land on a runway.
So next we'll just show a few examples of different potential propulsion methods that we'll have for rockets in the future. So this is nuclear propulsion, and we have a little video. Liquid propellant, most likely hydrogen, is pumped through the reactor core. Then fission generates heat. Uranium atoms split apart inside the reactor core and release heat from fission. Propellant heats up and expands to a gas. The gas is forced through a nozzle to produce thrust. The advantages over chemical rockets, the high energy density allows for broader launch windows and the ability to abort missions. More efficient, it's twice the amount of thrust force per flow. I hope you all read that quicker than I could say it, but yeah, so moving on. Ion propulsion.
So how do ion thrusters work? It's actually pretty weird and totally sounds like science fiction. Instead of hot gases, ion thrusters eject ions, which are atoms or molecules which have an electrical charge because they've lost or gained an electron. In the case of an ion engine, they're emitting positively charged ions, which have lost an electron. Once you've got ions, you can direct them with a magnetic field, accelerating them into space at tremendous speeds. So where do they get all the ions? The thrusters create them by generating a plasma inside the spacecraft, and they bombard neutral propellant atoms of some gas like xenon with electrons. These collisions release even more electrons from the propellant, turning them into positively charged ions. This plasma soup of electrons and positively charged ions has an overall neutral charge. The electrons are held in the chamber, leading to more ionizing events, while the positive ions are siphoned out through a grid at the end of the chamber. As they pass through this grid, high voltage accelerates them out the back of the spacecraft at speeds of up to 90 kilometers per second.
So an example of a spacecraft that we've launched that has an ion propulsion, I don't know if any of you saw the credit in the corner, was the Dawn mission that went to Ceres and Vesta in the asteroid belt. Once again, if anyone has any questions, feel free to ask or drop them in the chat. And then warp drive, everyone's sci-fi.
Rumour has it NASA is actually working on a real faster-than-light warp drive. So when do we get our first Starship? Faster-than-light travel is a staple of science fiction. Star Trek warp drives zip around the galaxy at hundreds of times the speed of light, but travelling at the real cosmic speed limit of 1 times the speed of light would make for some pretty dull sci-fi. I mean, it would have taken Han Solo 40 years to make the Kessel Run in 12 parsecs, travelling at only light speed. It's understandable that both physicists and sci-fi fans dream of cracking FTL travel. Spanish physicist and sci-fi fan Miguel Alcubierre was so inspired by the idea that he decided that the Star Trek warp drive should become a reality. In fact, he was inspired by Gene Roddenberry's choice of the word warp. Alcubierre constructed a warp field in the mathematical language of Einstein's theory of general relativity, a real solution to the equations of GR that would actually allow faster-than-light travel. Yep, pretty much the ultimate in fan fiction. But is it actually fiction? NASA doesn't seem to think so. Its EagleWorks Laboratories is actually trying to produce and detect warp fields. More on that later, but if NASA's researching it, it must be legit, right? So when are we going to be warping around the galaxy? Let's break this idea apart. First, it's important to note that this idea does not contradict the principle of a cosmic speed limit. That limit, the speed of light, refers to things, mass, energy, information, travelling through space. However, according to general relativity, there's no limit on the relative speeds of 2 separate patches of space-time. For example, as we talk about in this episode, the expansion of the universe means that very distant galaxies are moving apart from each other faster than light, even if the galaxies are relatively still in their local frames of reference. Also, below the event horizon of a black hole, space-time cascades towards the central singularity faster than light, carrying light, matter, monkeys, and everything else with it. Now, the space-time around and within a black hole is predicted by solving Einstein's field equations around a point of extreme positive energy density. Basically, mass and energy tell us how space should warp. But if you're cheeky, you can actually just make up a solution to the equations of GR without starting with a real mass-energy distribution. That's what Alcubierre did. He developed a space-time description, a metric tensor, that describes a volume of nice flat space-time enclosed in a bubble of extreme curvature, a pinching or warping of space-time in the surrounding shell that causes space to expand behind and contract in front of the bubble. As a result, the bubble is pushed and pulled by space-time itself, moving at speeds only limited by the intensity of the warp. A starship inside the bubble is carried along for the ride while feeling no acceleration at all. It's sort of like building a conveyor belt out of space-time. You stand still with respect to the conveyor belt, but the belt itself moves faster than light. But is this even valid? Can you just make up a space-time description and then essentially solve the Einstein equations backwards to figure out what arrangement of matter and energy would be needed to create it? It's sort of like giving the answer before you have the question. So, 42. Yeah, sure you can do this. There's just no guarantee that the resulting mass-energy distribution will be physically meaningful. In fact, when you try to do this for the warp field, you find that you need to produce a ring of negative energy density in a band around the ship to produce the right warp bubble. That means our ship looks something like this, in order to produce a space-time curvature like this. Unfortunately, it may not even be possible to make negative energy densities on large enough scales. We can create something like it, a negative pressure, on quantum scales via the Casimir effect. But on macroscopic scales, you'd probably need some sort of exotic negative mass matter, like element 0, which is tricky because there may be no such thing.
Yeah, so that was just a clip explaining how some of the warp drive would in theory work. And then we have a little clip on how do rockets work.
The body of a rocket is composed of different sections, all of which are housed within the frame of the rocket. The first component is the payload system of the rocket. For the uninitiated, the payload is the rocket's carrying capacity. The payload depends on the type of mission the rocket is being used for. It can consist of cargo, a satellite, a space probe, and even a spacecraft carrying humans. So, if you want to send humans to space, the payload of your rocket will contain a spacecraft. Whereas if you're using the rocket as a weapon, then the payload would consist of a missile. Next is the guidance system, the system which ensures that the rocket stays on its intended trajectory and goes where it's supposed to go. The guidance system consists of onboard computers and sophisticated sensors, as well as radar and communication systems to maneuver the rocket while in flight. Last is the propulsion system. A majority of the entire length of a modern rocket is actually made up of the propulsion system. As the name suggests, the propulsion system consists of the components that help launch the rocket off the ground and subsequently propel the rocket in a given direction. So how is this huge, enormously heavy cylindrical metallic tube shot into space? In order to get into space, the rocket must first cross the thick layers of atmosphere that envelop our planet. Since the atmosphere is thickest near the ground, the rocket has to go extremely fast in order to get past this part of the atmosphere. So how does it climb so fast in the air? The answer to this question lies in one of the most popular physical laws of the universe, Newton's third law of motion. According to the third law, every action has an equal and opposite reaction. In our case, we have a rocket that we want to launch into space. How does the third law help us? This law tells us that if we can get the rocket to push against the ground with an enormous amount of force, then the ground will respond by pushing the rocket upwards with an equivalent amount of force. That's where the rocket engine comes into play. A rocket engine works by burning either a liquid or solid fuel in the presence of an oxidizer. When the combustion reaction occurs, it throws out a great deal of mass as a byproduct of the reaction. These byproducts are released at great speed through the bell-shaped nozzles that you see at the bottom of rockets. Since the rocket pushes the exhaust down, the exhaust responds by pushing the rocket up at great speeds, which lifts the rocket off the launching pad and propels it upwards into space.
Yes, that was just a brief breakdown on how rockets work. Now we'll talk a little bit about some orbital mechanics as well.
Sorry, I'm unmuted now. All right. So when we're talking about orbits, that's basically when we're talking about an object that's gravitationally bound by something else. So gravity is making it so that that object can't escape, but the first object isn't going to collide with that one. So if you just throw a ball up into the air, or if you launch a rocket straight up, eventually it's going to come back down and collide with the Earth. But if you have a body that gets high enough up and is also traveling fast enough in a direction sort of parallel to the ground, then you can get into an orbit. And those are pretty well described by Kepler's laws of planetary motion. So Kepler's 3 laws. The first one says that orbits are ellipses. So orbits aren't usually perfect circles, or if they are a perfect circle, then it's still a type of ellipse, because a circle is a special type of ellipse, just like a square is a special type of rectangle. So basically what that means is that an orbit is shaped like an ellipse or an oval, and the center of mass, which is sort of where the middle of the mass between the two bodies in the system is at what's called the focus of the ellipse. So you need to know a little bit of geometry to understand what that means. Basically, the way we define an ellipse is as all the points that are the same, or sorry, you take like 2 points in space, and those are the 2 focuses of the ellipse. And then if you look at all of the points where the distance between each of those 2 focuses adds up to the same number. So you have this constant number, and you take the distance from some point in space to those 2 ellipses. And if that sum of the distances remains constant and you find all of those points in space, then you have an ellipse. That's basically the geometric definition of what an ellipse is. So one of those foci in an orbit is going to be where the center of mass is. So if you're talking about something like the sun and an asteroid, say, where the sun is much, much, much more massive than the asteroid. An asteroid is very small compared to the sun. Then the center of mass is going to be almost exactly in the center of the sun. But if you had 2 stars, say, like a binary system, and you had 2 stars of equal mass, then the center of mass is now going to be right in the middle between them. So the focus, or the point that object is orbiting around, isn't always inside of a body. If you have 2 bodies that are around the same size, it could just be out in the middle of space. But either way, you're going to have an ellipse, and that focus is going to be at the center of mass. So the second law of Kepler's 3 laws is that when you're looking at a planet going around in orbit, it sweeps out equal areas in equal time. So if you look at those two sort of shaded in areas, and you look at the planet going through that part of its orbit, you can see that each of those is 6 months long to get from the starting point to the end point of each of those shaded areas. And when you find the area of each of those shaded areas, it's the same. So if you have two areas of equal, two regions of equal area in that orbit, then you know that those two regions take the same amount of time for the planet to go through. So what that means basically, when you look at the shape of the orbit, the planet is closer on one side of the orbit, and that means that on that side of the orbit, the planet is moving faster. And then when the planet gets farther away, out near the edge of the orbit, the planet is going slower. Because you can see on that picture there that the distance in the orbit isn't the same in each one, but the area is the same. And then the third law has to do with the orbital period, which is how long it takes a planet to complete its orbit. So for the Earth, the orbital period is 1 year. That's how long it takes us to go around the sun. And Kepler's third law says that the time of that orbital period squared is proportional to the semi-major axis cubed. So basically, if you draw this plus shape through the ellipse that goes through the middle, the semi-major axis is going to be from the center, where those two lines intersect, out to the further edge. So you can see on that third picture there, the part labeled A, that's the semi-major axis. And the part labeled B, that's the semi-minor axis, the shorter of those two axes. Yeah, so that's the semi-minor axis right there, B, and then the semi-major axis is A. Thanks for pointing, Alex. So Kepler's law says that you can figure out, basically how long the orbit is going to be based on how far away the planet is from the center of that orbit.
All right, so when describing different things in orbital mechanics, it's really important to know certain key phrases that define different directions and positions regarding everything. So Alex, if you go to the next slide, it has like a better visual of it. So some motions in space you could describe as prograde, which would be a satellite moving in the same direction of orbit as the direction for like a satellite or an object. Retrograde would mean moving in the opposite direction, as you could see by the little drawings and label diagram. Normal motion would mean that you're moving perpendicular and sort of towards the actual satellite body, or like up, and then anti-normal would be again perpendicular in the opposite direction. Radial in means that you're moving towards the actual satellite in your motion around it, and anti-radial means moving outwards. Other two key terms that you could use are, Alex, if you go back to the other slide. Yeah, are periapsis, which means that it's the point where the orbiting body and the object that it orbits are like the closest point, and apoapsis, which means they're at the farthest point. So again, some key quick terms that help define an orbital mechanics.
And then I think before we go on to the next slide, I actually just wanted to show some of those orbital parameters and directions in Kerbal Space Programs. So Alex, if you can give me screen sharing, do I have that? Okay, yes I do. All right, can you all see my Kerbal Space Program window now?
It's loading.
Yeah, it looks good now.
Okay, you can see it. All right, so what we've got right here is I've got a spacecraft, this little gray triangle, in orbit around basically the in-game version of Earth. So you can see this blue line here is our, oops. There we go. This blue line here is our orbit around the planet right now. And you can see apoapsis, that's our farthest point from the planet in the orbit, is at about 2 million meters, and periapsis is also around 2 million meters. It's a little off in each one. So then if we look at the maneuvers that we can do, so that's basically if we use the thruster on our spacecraft and we want to fire it in each one of these directions, let's look at how that affects our orbit. So first, if we fire prograde, which that means we're firing in the direction that we're moving. So if we pull that one out, you can see the other side of the orbit, this dotted line here, that's our new orbit after we fire our thruster in that direction. And if we fire it for longer, the other side of our orbit gets farther and farther away. So our apoapsis moves around to the other side and gets larger and larger. So then if we do the opposite thing, if we fire retrograde, which is in the opposite direction of our orbit, then the opposite thing happens. The other side of our orbit gets closer and closer to the planet. And if we do that enough, then our orbit is going to intersect with the planet. So you can see our periapsis disappears because now our orbit goes through the planet. So that might be what I do if I'm trying to land back on the planet. I slow down enough that my orbit intersects with the planet. So now if we reset our orbit here, looking at those other directions, now normal and anti-normal, so that's sort of like up and down. So if my spacecraft is moving this way, so if you look at the direction of the orbit, it's moving left to right on this screen. So if I fire up in the normal direction, then I'm going to change the inclination of my orbit. So now my orbit is tilted with respect to how it was before. So I fire up, which means that my spacecraft is going to go up on this side, and then as it goes around the orbit, it's going to go back down. So obviously, if I fire anti-normal, the opposite thing happens. Our orbit gets inclined in the other direction. And then if we fire in the radial directions, now what happens is our orbit sort of shifts left and right. So if I fire radial in, my orbit sort of shifts to the left. And if I fire radial out, my orbit shifts towards the right. So that's a quick demonstration of what each of those directions mean when you're talking about a spacecraft firing its thrusters to adjust its orbit.
Do you want to just keep sharing the presentation from your computer?
Oh yeah, I can do that, sure. Let me get back to Zoom. There we go. You should have the presentation back now, right? Okay. Just a second. There we go. All right. So we got through that. So now orbital maneuvers. So that's kind of what I was talking about before, is if you fire your thruster and you change your orbit, that's called an orbital maneuver. So basically there are two general types of thrusters that you would use for orbital maneuvers. And the first one is called reaction control system, or RCS for short. So those are like small multi-directional thrusters. Basically, you'd have a bunch of little groups of thrusters all around the sides of your spacecraft. And you'd use those thrusters if you're trying to turn yourself so that you can use your main thruster, or if you're trying to dock with another spacecraft, you have to do a lot of really fine adjustments to your orbit to line up with it perfectly and match its speed perfectly. So that's what you'd use an RCS thruster for minor orbital corrections, for docking, for turning your spacecraft, things like that. And then the main thruster, that's, generally you'd have one big thruster on the back of your ship, or you might have a group of thrusters, but basically they're only going to fire in one direction. Or if they are able to turn, it's maybe only a few degrees. So basically you'd use your RCS thrusters to turn your ship and line yourself up in whichever direction you want to fire your main thruster. And then you'd use the main thruster to actually change your orbit. So that's if you're trying to move into a much higher or a much lower orbit, or if you're trying to move out of orbit from one body to another body. So say you're in orbit of the Earth and you're trying to get into orbit of the Moon, you'd use your main thruster for that to get out of the Earth's orbit and into the Moon's orbit. So if you're trying to perform like a major orbital correction or change between bodies, that's what you'd use your main thruster for. And then when we're talking about thrust and changing your orbit with a spacecraft, you usually talk about something called delta V, which is exactly what it sounds like. It's change in velocity. But basically, it's a measure of how much your spacecraft can change its velocity with the amount of fuel that it has left. So that's used for calculating orbital burns and things like that, or if you're planning a mission and you're trying to figure out how much fuel and how much thrust you need to complete that mission, you would figure out how much your spacecraft needs to change its velocity, starting at 0 on the ground, how much velocity it needs to get into orbit around the Earth, and then how much you need to change your velocity to, say, get out of Earth's orbit, and how much you need to change your velocity to move towards Mars, and then how much you need to change your velocity to slow down at Mars so that you don't just crash into it if you're trying to land on Mars or something like that. You'd calculate the total amount of delta V that you need for the mission, and then you can use that to plan how much fuel you need, how big your rocket needs to be, things like that. And then gravity assists are another type of orbital maneuver that are used pretty commonly, and they're very efficient because basically you don't need any fuel to do them. You're using the gravity of another body that's already in orbit, usually a planet, to help you change your own velocity. And those were used in the Voyager missions, and we have a quick video here on how that works.
For decades, NASA has stolen gravity from neighboring planets and used it as fuel for deep space exploration. It's called a gravity assist, and because of it, we've been able to travel to regions outside the solar system that would otherwise be unthinkable. So how does it work? In a nutshell, a gravity assist is a technique that changes the spacecraft's velocity relative to the sun by swinging through the gravitational field of a planet or moon. To accelerate, the spacecraft flies with the movement of the planet, picking up a small chunk of its orbital energy in the process. To decelerate, the spacecraft flies against the planet's motion. The larger the planet, the stronger the gravitational power, meaning the spacecraft gets a bigger push or pull, all on the dime of the planet's gravity gas card. The first flyby technique can be traced back to the Voyager missions of 1977. At the time, the two unmanned spacecraft were launched into space to study the gas giants, Jupiter, Saturn, Neptune, and Uranus. But the distance to Jupiter is deceptively long, only about halfway to Saturn. And the vehicles the probes were launched aboard, the Titan III Centaurs, could only provide enough energy to get them to Jupiter. The launches, of course, were planned so that Jupiter aligned perfectly with the spacecraft's route. The orbital designers targeted the closest approach distance to achieve the desired speed. Afterwards, the probe's momentum pulled them away from the planet. Voyager 2 toward Uranus and Neptune, and Voyager 1 toward the limits of the solar system. On August 25, 2012, Voyager 1 became the first human-made object to enter interstellar space. As NASA puts it, further than anyone or anything in
Cut off the end of the sentence there. But yeah, so basically a gravity assist is where you use a large body and you plan your mission so that that body is going to be somewhere that you're passing by already, and you're going in the same direction as that body's orbit. And then you wait for that planet or other large body to pull you in the direction it's going, but you're going fast enough that it can't capture you and pull you into orbit around itself. It just pulls you and it gives you a bit of a boost in the direction it's already going because of its gravity. All right, so now we are going to be going into Kerbal Space Program again, and we are going to be showing you how you can sort of construct a rocket using this program. It's a really fun program that you can use to build rockets and to plan missions and things like that. It uses a lot of the principles that we talked about, things like delta V, things like thrust and orbital maneuvers and all of that. And we are going to try to go to, did we decide on Duna, Perry, or are we going to go to the Mun?
Well, I mean, I tried. I mean, the one might be easier, but I mean, I don't know. We could try Duna. I think. I mean, right before the GBM today, I tried to get to Duna and Kerbal, and I was able to get there without too much trouble.
All right. Well, do you want to stream the game and you can pick which mission we do?
Yeah, sure.
All right. So now we're going to have Perry stream the game. So before we go to that, are there any other announcements or anything we had, Alex?
I don't think so.
Okay. All right. So then, all right. Yeah. So everyone, please sign in. The links to sign in are in the chat. I sent them earlier. And that's sort of the end of our main presentation. But now we're going to move on to the mission part. So if you'd like to stick around for that and help us plan out and execute our mission and see how all of that works in Kerbal Space Program so that you can maybe download it yourselves and try it out. It's a really fun game. So we'll move on to that now.
So we have a question from Henry Shee. What programming languages do rockets tend to use? Does anyone know?
I don't know.
I know that the Saturn V rockets in the 60s, I don't think they used a programming language. I think that they actually had the code like hard coded into like hardware, which is kind of neat. I don't know what modern rockets use though.
Didn't they used to use punch cards? Or is that not a thing?
We're talking about like.
I know they did use punch cards for computers that they had on the ground that were performing calculations basically for like orbits and stuff like that, so that they would know how long each rocket burn would be in each stage of the mission. But I think at the time of punch cards, computers were too big to be able to fit in the small rocket capsules. So I know what they used on the Apollo missions. It's actually kind of cool. They used these like wire loops, and then they basically like weave the wire through them. And they used they hired a bunch of women who are like skilled weavers, like weaving fabric, and used them to like weave these wires through all these little magnetic loops to basically hard code all the logic circuits and stuff like that into the capsules. So it's really kind of a cool process if you want to look that up and learn more about it. It's pretty interesting.
Any other questions? Okay, then I guess we can move on to the Kerbal demos and building and flying.
So now I will get Perry's stream pulled up here.
Yeah, I'm streaming on the Discord channel right now, if you want to look at that. But also for, if you don't want to do that so it's easier, Henry's going to screen share my stream on Zoom.
Yeah, it's kind of interesting. We found that the way to stream a game with like the least amount of stuttering and lag is actually if one person streams it to Discord and then another person in the meeting screen shares Discord to Zoom. Because I guess Zoom's like video capturing of games is really bad. So if you just try to stream the game to Zoom directly, the frame rate is really low and there's a lot of lag. But if Perry streams it to Discord and then I screen share his stream from Discord to Zoom, it works better. So you can either watch it here through Zoom or you can go watch it through the Discord channel, but I think we're going to be staying here in the voice chat in Zoom. So probably easiest to just stay here. Looks like you've got a moon launch set up there, Perry?
Yeah, this can go to the Mun or to Duna.
All right. Do you want to maybe go into the vehicle assembly building first and just sort of show us all the parts that go into this?
Sure thing.
Yeah, so in the game here, you're basically running a space agency, sort of like NASA, but you've got your own space agency. You've got a big plot of land here. You've got a vehicle assembly building where you build your rockets. You've got a mission control room. You've got your launch pad where you launch them from. You've got astronaut center where you hire new astronauts. It's a pretty cool game.
And I just realized I should put on just.
Yeah, so basically what you're seeing on the left there, there's a menu of all the different parts you can get. They're sort of divided up by type of part.
Yeah, sorry, this thing is just being a bit odd. That's not really important. Just, okay, there we are. Okay, so this is the rocket I've put together. It's gonna go layer by layer. So the top stage over here is our lander. It has a few things on it. We have the capsule, where our astronauts are going to be. We have some parachutes, one main parachute for when we land back on Kerbin, which is the analog of Earth. We have some other parachutes if we want to try to land on Duna, because that has an atmosphere. There's also some solar panels over here for electricity, which we need. We have a ladder for getting out. We have landing legs, lights, and batteries, and pretty much, and then this entire cylindrical structure that is all around is the fuel tank. Okay, that's all being held inside something called a fairing, which is for aerodynamics. Once we're in space, this entire shell is going to break off. Underneath that, we have a lifting vehicle. This has multiple stages like the Saturn V. So we have this stage over here, which has RCS thrusters on it, which we talked about in the presentation. And we also have an SAS system, or a stability assist. I forget exactly what it stands for. It helps keep the rocket pointing where you want it to point.
Yeah, I think it's stability assist system is what it stands for.
And underneath that, we have an even bigger lifting vehicle. That's pretty much the rocket.
Yeah. And it's pretty similar to the actual Saturn V rockets in terms of the stages and the shape and things like that.
Yeah.
I think the one major difference between this and the Apollo missions is that the final stage that sort of ended up in orbit would then have two smaller stages. You'd have the command module, which they'd go to the moon together. You'd have the command module and the lunar module, the LEM. And those two would dock together in space, fly to the moon and orbit around the moon together. And then the LEM would break off and go down and land on the moon while the command module stayed in orbit. So one of the three astronauts on the Apollo missions would stay up in orbit around the moon in the command module, and the other two would go down in the LEM. And then at the end, the LEM would come back up. It would launch off the surface of the moon, dock with the command module, and then the command module would fly back to Earth and go down through the atmosphere. Parachutes would come out, and it would land safely in the ocean.
So, yeah, so the reason we're not doing that is because rendezvous, at least for me, are kind of really finicky and annoying. I don't know if it's easier for Henry than it is for me.
They're a little tricky in Kerbal Space Program, as they are in real life, I'm sure.
Yeah. So the first thing we have to do is to get this thing into orbit.
Do we want to have a countdown to launch?
Sure.
All right, let's have everyone turn on their microphones so we can count down from 10 to launch this. All right, everyone ready? I guess the synchronization won't quite work with Zoom, but we'll see how it goes.
Yeah,
this is gonna be fun.
10, 9, 8, 7, 6, 5, 4, 2, 1. Ignition.
Ignition.
Astronomy Club. You know, it's helpful when you have a Houston here.
Oh yeah.
Hey.
If you have any problems, we'll call you.
Yeah. So like we talked about in the presentation, the rocket has to get high, but it also has to be going really fast horizontally. So
it has to get high, Perry.
It has to get super high.
They call Snoop Dogg.
Yeah.
He goes high.
Yeah, so the way I'm flying it is it's getting a vertical velocity and getting higher, but also going faster to the side.
Yeah,
So
I can kind of see like the arc that it's kind of making.
Yeah.
Ooh, look, there's the moon right up there. Or the mun, as it's called in Kerbal Space Program.
Wait, is that someone's...
Wait, who's listening to Trump?
Watching the news in the background.
Yeah. I think it was Henry. Yeah.
Oh, Henry.
This is our Space Force rocket.
Yes, the Uranus 6. Even better than the Saturn V. So much better. It's the best rocket they ever made. I made.
I can't do the accent, so just have his head.
Ooh, lots of thermal heating there from the atmosphere.
I look orange.
Yeah.
Right?
Yeah.
There we go.
Yeah, this little maneuver is actually called a gravity turn because gravity is helping push the rocket.
All right, I think the rocket's kind of hot. Right?
Yeah, that happens. Don't worry about it. It'll
Jebediah
buff
is
out.
fine.
Yeah, Jeb's fine.
I haven't
Just
called
make
me
sure-
yet, so no problems here.
Yeah, just make sure not to detach the fairing before you get out of the atmosphere if you're
God, it's
flying a
getting really
rocket.
hot.
Yeah, or else your top stage will burn up.
Because I'm Batman.
I mean,
the Justice League station.
Well, I guess it might survive.
Yeah.
The parachutes might burn off. You might not be able to land again.
Yeah.
Fortunately, I'm one of the few people here who are not rocket scientists, so.
What major are you?
Well, crashing is a form of landing.
Oh, yeah.
I mean, astronomy and rocket science aren't the same thing.
Yeah. Right.
You know,
Okay.
that's more of an College of Engineering and Applied Sciences major.
I feel like rocket science isn't even real. It's just used ironically.
There we go. We've got our
Rocket
stages
science
separating.
just
Yeah,
applied
stages
kinematics.
separated. I'm going to detach the fairings.
Very explosive.
Very explosive. Open the solar panels. Both of them.
Now let's just open one. We don't need that much electricity.
Yeah. Yeah.
Infinite power.
Yeah. Right. So now what we have to do is we're going to go to the where the apoapse is.
Perry, I just want you to know my brother said he'd kick your butt in Kerbal, but since you've been playing for since this game came out and he only got it last year, I think you're gonna beat him.
I mean,
I don't think he's been to Duna before.
Yeah, so now if you see what Perry's doing here, he's preparing an orbital maneuver.
Yeah.
And then the RCS thrusters there, rotating the ship.
Yeah.
Sorry, go ahead.
Yeah. Along with it's also being helped out by the SAS system.
Yep. So then if you look at the bottom of the screen there, that orange and blue ball, that's called the nav ball. It's sort of the same thing you'd have on an airplane. It sort of shows you your directions relative to gravity, which direction you're facing, and it has a bunch of little markings on it that move around as you're going. So that yellow circle, if you can see it there, that's prograde. So that's how you know you're going in the prograde direction. And then it also has retrograde, normal, anti-normal, radial in, radial out, and then a couple of other ones. It has a maneuver button so that when you're setting up a maneuver, you can have the pilot of the ship automatically point it in the direction you want to fire your main thruster. And then it also has a couple for target. So that's if you're trying to dock with something, like if you had a space station in orbit and you're trying to dock with it, you can have your ship point itself towards the station, basically.
Can we dock with the Justice League station?
Yeah.
If you build the Justice League station and put it in orbit, then you can dock with it.
And as I'm firing, you can see the orbit getting higher and higher. The periapsis is actually above the, above the atmosphere.
The periapsis?
The periapsis. Yeah.
Say, if you build enough ships, can you create a Dyson sphere around the sun? Just keep coupling them all.
The game might crash.
Yeah. your computer probably can't support that, but...
Or maybe just a ring above the Earth or something.
Turn it into
You might
Halo.
be able to.
That'd be a lot of assets to render.
Yeah, the computational power you'd need would go up dramatically as you try to add more and more parts. But if you have a beefy enough computer,
part scaling thing,
you might be able to do it.
Yeah,
it's that each part is like a kilometer long or something. Then you might be able to do it.
Yeah.
So right now we have to decide whether we want to go to the Mun, which is over here, or to Duna, which is, hold on.
Mars?
Over here. Yeah, the Duna equivalent. Yeah, Mars equivalent.
All right. Is there a way to do a chat poll?
Is there?
You can do a poll in here. I just don't know how.
How do we do it? I think
do
Alex is the host, right? Would he have to do it?
We can message him.
Have people react on Discord.
Oh yeah, we could make a host and have two different emotes.
That'd be something.
Henry, are you not the host right now?
I think Alex is still the host. Or here, we can just do this. So if everyone's in Zoom, if you click on the participants button at the bottom, then you can do like reactions, or if there's like a yes, no, something like that. All right. Can everyone see that?
Yeah.
Yeah.
All right. So how do I pull it up? There we go.
Wait, where is it?
If you go to like the bottom of your window where you have the video chat, click on participants, and then there are different buttons you can react with. So let's say react with yes if you want to go to the MUN, and react with no if you want to go to Duna.
Okay.
Oh, also just a fun thing about Kerbal is
You just did a raise hand. What does that even mean?
I'm expressing my own individuality, so.
Rob, no.
It
no.
means go to Miss.
We don't need that here, Rob.
Shit,
Stop.
I need a break.
I mean,
Wait,
you
which
have,
reaction is which again?
you said you used the parachutes because Duna had an atmosphere, right? The MUN doesn't have an atmosphere.
Yeah.
Might as well put that to use.
Yeah.
It's for redundancy.
Well, I don't want to activate the last parachute you got before you get back to Kerbal.
All right, so it looks like we have 6 votes for the MUN, and 1, 2, 3, 4, 5, 6, 7, 8, 9 votes for Duna.
Hey, Duna.
All
Here
right,
we
Duna
come.
it is.
Cooler.
Okay. This is a bit more involved though. So with the MUN, what you could do is you could just as an example, just increase the apoapsis of your orbit, like we did when we were getting into orbit. And eventually, if you make it big enough, and you fire your boosters at the right time, you can get an encounter with the MUN. Here. And then you just get close enough, and when you're close to the MUN, you would fire your boosters again retrograde and get an orbit around it. And then you can land like that. But with Duna, it's all the way over here. So you can't exactly do that. Well, at least not as easily. It's the same principle, but there's a certain window of time when you can do that. Kerbin and Duna have to be at a certain angle to each other, which is not this angle. So I'm just, how fast can this in time work? Okay, good. Right. So Kerbin and Duna have to be at about a 45-degree angle, with Duna being in front of Kerbin around like over here. That may take a hot second actually, now that I'm looking.
Yes, so I'm actually going to switch the screen share off of Discord for a second, just to show you a cool tool here. And get back to Zoom. Okay, so now let me share Chrome here. So this is an interactive illustrated interplanetary guide and calculator for Kerbal Space Program. So basically what this is doing is it takes the parameters of all the objects in Kerbal Space Program, and it can basically plan your orbits for you and plan your missions. Like when is the most efficient time to launch to get from, say, Kerbin to Duna, which is what we're trying to do now. So it'll show you here on this diagram on the right. Let me zoom in. Ooh, that didn't do what I wanted. Okay, yeah, sorry, on this picture on the left here, so this is showing you Kerbin and Duna in orbit around Kerbal, which is the sun of this solar system, and it shows you what angle you want them to be at to have the most efficient transfer between the two. So you could launch at any time and get between the two, but at this time, when they're at this angle, that's the most efficient time to do it.
Yeah, it's actually kind of funny because there's a lot of Kerbal Space Program. This is about 45, right? You think? Maybe.
Back to it real quick.
Maybe a bit more.
Let's go.
It's about 45.
Yeah, looks pretty close.
Yeah. Right, so then what we have to do is we go back in over here. And what was that angle, launch angle that you have to do?
Let's see. The launch angle was, the ejection angle is 151 degrees.
So that's like over here, about.
Yeah, about there.
Oh, okie dokie. So what we're going to do is we're going to increase our apoapsis until we're free of carbon. You can see over here our trajectory. And we just have to fine tune this until we get close to Duna.
Yeah, so basically what Perry's doing there is he's accelerating fast enough that he gets out of Earth's gravitational area of influence, and he's putting himself in an orbit around the sun instead. And then he's adjusting that until it lines up with Duna, which is where we're trying to get to on the other side of our orbit.
Yep.
And this is the same reason that in real life, when you're talking about launching rovers or other things to Mars, there's a certain launch window that comes around, I think, every 2 years when everything that's going to Mars is launched, because that's when the planets are lined up, like they are in Kerbal Space Program, but at the right angle for our solar system, so that you can launch out of Earth's gravity and intersect with Mars, which you're trying to go to once you get around to the other side of the orbit.
Yeah, hold on, this might take a sec. I should be able to get it though. Yeah, you see, these two little areas over here are us closest approach to Duna. We want those to be right on top of each other. Come on now. Come on. Oh, there we are. Okay, that's pretty close. Yeah, now we just have to fine tune it. So our closest approach will be about 229,000. Really? Is that right? Okay, I guess.
That seems pretty close.
Yeah, but it's not showing a periapsis, which I'm finding weird.
A peri? Oh, we already made that joke.
Yeah. Okay. So I know how we can test this out. I'm a quick save. And if this thing doesn't work, we can just rewind. Exactly what NASA can do.
Yeah, exactly.
Yeah.
Maybe they just simulate their missions first in Kerbal Space Program.
And I kind of thought NASA just wings it.
I mean, I think there is software out there to like simulate orbital mechanics and stuff that NASA probably uses.
Yeah, and it's probably slightly more advanced than Kerbal Space Program. A game available
Slightly, that's an
on Steam
understatement.
for $20.
It's actually kind of neat, though, is I've seen pictures of, I forget, some important people at NASA's office, and they have, like, Jebediah, like, on their shelf, like a plushie.
Nice.
Yeah. Okie dokie. Now we're just waiting for the burn to finish.
Yeah, so that main thruster is firing.
You announced it yesterday.
Yeah. I thought of that while I was saying that sentence.
Oof.
Yeah.
I've said in the chat.
All right, looks like the burn is almost complete, and then we'll be able to just time warp around to our intersect with Duna. We don't actually have to wait 8 months or whatever it takes in real life.
I mean, we could.
We could
If
sit
we
here
want.
for 8 months and wait for this to happen, but
Yeah, we could wait out the virus.
Yeah.
Okay, so we don't really have an approach yet. But what the hell?
Barry,
Oh.
you curse. You're too pure.
No, that's not a curse. That's a place.
Don't impose your views on me.
It's not a curse, it's a word.
Yeah. Yeah. That's not. I'm playing Animal Crossing while we wait. One of my villagers gave me a stark white traffic cone. Why? Where am I gonna put that?
I kind of want to play Animal Crossing, but I don't have a Switch, and they're all sold out everywhere now.
So the phone app, it's free for Animal Crossing. It's not as good.
I
I was
Switch,
gonna
but
say
like,
the
I don't
phone.
have the time to play.
I don't have a Switch. My brother has a Switch, and like he plays Animal Crossing, and the phone app is just not the same.
No.
Yeah, I don't trust mobile gaming in general. That's why I get games like Kingdom Rush on Steam.
Can somebody explain to me the appeal of a video game about doing chores and being in debt to a raccoon?
It's better than being in debt in real life.
I was gonna say.
It gives you a sense of accomplishment.
Which you can't get in real life.
But like,
Lana, do you have Animal Crossing?
However,
I just split it with my brother, so I haven't started playing yet, but I do own it, technically.
Okay, I can give you fruit.
Yeah, I'll probably put in the Discord when I start my friend code or whatever the hell it is.
Yeah, friend code. I just sold a selling box, so you're out of luck there, but I can get you one easy.
Wait, what's Animal Crossing actually about?
Basically what Dan said, but more.
It's a little bit like Stardew Valley.
Yeah, it's just like Stardew Valley, yeah.
Oh, really?
The
I
same
should
job.
get it then.
Planting
Yeah.
stuff. You're just looking for resource. The new one's a lot like Minecraft. You look for resources and craft them. But which is refreshing because you don't need to buy everything now. You can actually make it yourself. So it's and you can play stuff outside now. So you can decorate your islands as much as you want. It's great. I think Alana has said it. So were you talking about Switches or who said is Animal Crossing in stock or Switches sold out?
Switches are sold out.
Oh, I have a Switch Lite, so.
Yeah, they're all sold out at like Amazon, eBay, Target, everywhere.
Yeah.
You can get them on eBay for like $500, but I don't want to pay $500 for a Switch.
Ooh, okay. Okay, so.
Yeah, I might end up getting
I mean, Killian had a good response. Actual life self-loathing. And it is a negative exponential curve. Actually, no, it's an exponential curve.
with respect to time.
With respect to time, yeah.
you see,
It's like we're moving
I've
through our
played
orbit
50
here.
hours of Witcher in the last week.
50 hours?
50 hours, yeah.
Wait, do you have the
Yeah, that much time.
Alana, she does. Just can't do it.
Wait, what?
You looked very done for a second.
It's just a shocking number.
Yeah.
wait, do you have the DLCs?
I have, I think I got the Game of the Year edition.
Oh.
So it came with Hearts of Stone and Blood and Wine expansions, and I think all the free DLC.
So my brother has it, so I Steam share with him.
Hey,
Started
why don't
playing
we-
Minecraft this week.
Who started playing Minecraft?
Me.
Rob?
Yeah.
Oh, that's cool. I have a server, Rob.
Oh, do you?
Yeah. I
It's
tried to. I'm Mesophere Jones on Discord. I tried to add you.
It's a very addicting game, unfortunately.
Yeah, I've been playing a lot of Minecraft too.
You see new nether biomes?
I'm
I have not yet.
found a
It's only a snapshot.
yeah, I just got a lodestone, so I'm gonna put it like 500 blocks away where I found a Soul Sand Valley. And I
Imagine if the lodestones actually had magnetic properties and you could conduct magnetic experiments in Minecraft.
That would be
That is the road to giant-ass robots destroying everything.
And induce redstone signals and
And spiral redstone staircases.
How's the intercept with Duna looking there, Perry?
agree with
We
that
can't
a lot.
quite read the numbers on the stream.
So
Yeah,
if this
it's being a bit
coronavirus thing
small,
keeps
but-
continuing, we're gonna have to do a junior lab in Minecraft. Is that what you're saying?
We could do the electronics and instrumentation lab using redstone, right?
Yeah, I've got basic logic gates.
Yeah.
And
Lab fee would just give everyone Minecraft copies of Minecraft. Win-win.
I mean, Henry, it'll probably work better than the actual stuff they give you in junior lab because all of it's fucking broken. So.
That's not reassuring.
They last updated the stuff from Stony Brook when we got all those Russian professors from the Soviet Union.
Perry.
Yeah.
You
Yeah.
remember our fucking multimeter that was reading 300 volts when there was nothing plugged into it?
Yeah.
Have you heard the
You've just gotta zero it out.
Oh shit. Okay, so I may have accidentally set our course to fly
Where?
into the planet.
Well,
don't
then
worry. Don't worry
we
about
just
it.
need to slow down before that happens, right?
No.
Yep.
All right, are we gonna time warp up there?
Let me just. Okay, is that? Okay, I moved it so we're not flying into Duna. Okay. Anyway, yeah. Let's time warp. So we're close. Okay. Sorry, that's a bit of orbital corrections needed.
100,000 times time warp.
Yeah, there's a clock in the top left. You can see, and you can see us over here and Dune over here getting closer and closer and closer.
Oh God, we're gonna hit it. Oh no! Oh no!
Oh God,
Just
oh
quick
fuck.
save. We're getting closer.
We name our
Wait,
whole.
is there like an auto quick save button?
I just quick. Yeah. It's F5
Oh, nice.
and
Did not
F9
know that.
reloads.
Are we
And,
the whole? We're gonna smash into that planet.
No, I switched it, so we're just gonna graze it.
I mean, we may or may not like you when you're angry.
Yeah, we don't like Perry when he's angry. What?
Yeah, let's make it so we just graze it, so we could do some air braking.
Perry can be scary when he's angry.
Connor, we don't talk about that.
I have the photos. I have the evidence. Yeah, I post them in the Discord.
I don't know if that's a smart idea.
Then, oh, that's right.
I'm just saying we don't know what may happen.
Okay. All right.
Them's fighting words.
Are you threatening me, Master Jedi?
I'm scared of Perry.
Like how Space Cam now just shows his mouth like a true evil.
This guy's gonna fight for me. Look what he can do. Imagine this guy at a rock concert. Oh yeah. Anything and that's his brain.
Are we gonna get into orbit around Duna and then decrease our orbit, or are we just gonna fly right into its atmosphere?
Well, I mean, we should probably fly into its atmosphere first, so we could do the air braking.
Yeah.
Yeah.
As long as we don't burn up. Although
we
Duna's
should-
atmosphere isn't very dense, so.
Yeah. So I adjusted our orbit a bit, so we're just going to graze it.
All right.
Just a bit.
What's our approach apoapsis?
20K.
20K. All right.
Yeah, I hope that's not too low.
I'm just curious, how many of you have played Kerbal Space Program before?
Nope.
Anyone besides me and Perry?
Nope.
I had it and I
I
played.
have it. I haven't touched it yet.
All right.
Watched Ian play it.
I play it time to time, or used to.
Okay, so where's Duna? Okay, there's Duna. Okay, so let's time warp until we're close by. You can see Duna's one of Duna's moons orbiting around it, over there. Yeah. So before we actually get to Duna, we should probably tuck away the solar panels. We don't want them to burn up.
I think you're still in time warp.
Why are they not? Can they not?
You're still in time warp, Perry.
Oh, am I?
Yes.
Oh,
yep.
Thanks. Yeah, thanks. Wait, no, it's not. There's no option to close them. That is so weird. Maybe if I...
Oh, are those the kind that can't close?
I didn't know there were kinds that can't
I think
close.
there's one kind that's not retractable, and I think that's that one.
The lighter ones you can't retract. The ones with like a casing thing, you can retract those.
Yeah.
Oh.
Yeah.
Well,
Hopefully they don't burn up then.
Well, it's one thing to edit when you're on the ground.
Yeah, you don't even need electricity. Just... Okay. So now I'm going to maneuver us. So we're facing retrograde. So the engine is the one that's flying into the atmosphere.
Yeah, we don't care if the engine burns up.
I mean, yeah, we don't. Yeah.
You care if Mercury is in retrograde with us.
Intense 1812 overture.
Some lady sing the song Duna.
We need some thematic music.
I wish I could find my kazoo. I know where my kazoo is.
Oh, the solar panels broke.
Well, we can always Alt F12 and turn on infinite electricity.
You could. Yeah. Okay, so.
Can you all hear the dramatic music on my computer? Turn that down a little, so hopefully you can still get intact. This is Mars by Holst, for anyone who doesn't know.
It's very thematically appropriate.
Exactly. There's a whole suite by Holst. He has one for each of the 7 non-Earth planets.
Jupiter is awful. We read it one time in a band class in high school. Not one time.
Well, it's fun to listen to.
Yeah, but not to play.
No, I can't imagine this.
You read a song to the plants?
Sorry, what was that, Connie?
Who made the song and feature the plants?
Gustav Holst.
Yeah, Gustav Holst. And the reason that there isn't one for Pluto is because the suite was written before Pluto was discovered. I think the This suite was published in 1917, and Pluto was not discovered until 1930. But it's fortunate because now Pluto is not a planet, so there would be one too many movements.
Wanna say that to my face, buddy?
Okay.
I got a spear claw fast chat to your face on it.
All right, looks like we're in a pretty stable orbit of Duna now.
Well, we were.
Oh, now we're.
Now we're not.
Ah,
now we're
perfect.
going to land.
Nice.
Oh boy! Oh boy!
All right, we're time warping into the atmosphere here.
Again.
Yeah, viva little Pluto.
And then I guess we're gonna just drop this second stage booster on Duna's surface.
Yep.
We can litter on other planets. You know, we don't have to worry about cleaning it up, right?
Ooh,
Who
we
cares
got
about Duna?
Astro Club. We got. I thought after we get Europa. Say I haven't condensed Europa into this not so spherical blue rock.
Shiny.
Actually, not very. Why is it shiny? It is shiny. It's very chalky. You know, it's chalk. It's chalk.
So you can see our orbit getting smaller and smaller and smaller as the air braking bleeds off energy.
But I thought air resistance was negligible.
In a sane world, it is. We're on Duna now.
And now we are on a collision course with the surface.
Oh, yeah. No, this wasn't a good idea. Hold on.
Just fire that thruster real quick to slow us down.
Yeah, okay, hold on. Okay. I gotta... I have to throw on my... Okay. Parachutes are primed.
Parachutes are deployed.
Or those, yeah. You can see our speed gradually getting slower. Okay, that should be good enough. Okay. Okay. Now I'll just
make sure that altimeter is set to land.
Oh, yeah, I should probably do. Oh, that's a lot closer. Okay.
Yeah.
Okay. Now then, I'm going to detach that stage. We're going to toggle our gear. Okay. That's going to blow up real soon.
Boom.
Ooh. More parachutes. There we go. Now we're actually slowing down.
Yep. Look. Wait, look, you could...
Did one?
I don't know if you guys can see, but yeah, it just bounced off. It's 1,000 kilometers above us.
Or I guess maybe the explosion sent it back up into the air.
Yeah.
Nuclear powered manhole cover.
Okay. So I'm using the thrusters to slow us down now because there's not enough air. Okay. Gently. Okay. Okay. Oh God. Oh God.
Ooh.
Oh no. Oh no.
Ooh. Too soon.
Well.
Houston, you have a problem.
Okay.
Nice.
Good gosh, here though.
We are on the surface of Duna.
Wait. Where?
Someone's
Oh wait,
better than
wait.
I
Did that? Oh. Okay. Oh.
So, Perry,
That's a resilient little guy.
Perry, is there any possibility of
That guy has like 20
mission, or
cotton.
does Chev just live on Mars now?
Well.
Someone
we
better
have
than I
planted a
thought it
flag
was.
on Mars.
Wait, what should the site name be?
round off error.
Yeah. Okay.
In memory of the 52 casualties.
Okay. Wait, why can't I?
You have to put something in the plaque text.
Oh, do I?
Maybe, yeah.
Or at least you have to like click into the box. Yeah.
Oh, okay. Nice.
There we go.
Uh,
Well, we're not getting back off the surface, but we got here successfully.
Wait. Oh, wait. Oh, the door's underneath. Wait, no, it's not on the other side. Okay. Okay. Hold on.
That would be unfortunate.
It would be very unfortunate. Wait. Okay. Okay. F. Okay.
Right.
There we go.
Well, I kind of wonder, what if...
He just Spider-Man'd in there.
Do you have RCS on this?
I do not. Wait, hold on. I kind of wonder, what if I just fire my... Actually, wait, let me just quick save. Kill Jeb. Okay, wait, what if I just...
Kill Jeb.
Oh, wait, no, God, no.
Dead.
There we go. That's what I was expecting.
Oh, wait, Jeb is still alive.
Jeb is still alive.
He kept the pot intact through the sheer force of his badassery.
I'm not sure if I should reload that or not. You know.
Either way, it was glorious.
This is something I've been waiting for. Dab on him.
But look at his expression.
Oh, dang it.
Jeb?
He's
Jeb's
me if
fucking
I ever
funny.
landed on another planet.
I just noticed their spacesuits actually kind of look like the new Artemis spacesuits.
Oh yeah, they do. Wait, can I?
He's like,
Jeb's
I'm
just
alive.
vibing.
Oh yeah.
Oh, damn.
Fly back to Earth.
He's become Iron Man.
I mean, if you
Can
turn
he
on like
escape
the
Duna orbit using his little jetpack there?
I think he must be able to, right? If he has enough thrust to lift, then like theoretically he could get to orbit.
Nope. Just turn on infinite fuel.
Does this man even have a neck? To snap.
Does he need one?
Does he even have a neck to snap?
There's a neck there. You can see it if you
Can
move
it
the
snap?
perspective a bit.
Why is he
I don't
laughing?
think it can. No, wait, I think he actually might have snapped his neck. Because his mouth is now moving
He's got it.
in the way that people know he's alive.
Oh, he's fine.
Yeah. I'm pretty sure, like on the moon, he can actually get into orbit.
Are these Kerbals fucking tardigrades?
Yeah, pretty close.
Legs, nor do they have the right shape of mouth.
Wait, what?
Evolved tardigrades.
They need more legs. Tardigrades have like 8 legs, man.
They lost 4 legs because they didn't need 8. They didn't need 8 legs anymore after they became whatever the fuck that was.
Okay, what the?
They also need the alien sucker mouth.
Who's hesitating in there somewhere?
That's true. It comes out like a moray eel.
All right. Well, I think if our mission objective was to land on Duna, we had a successful mission.
I mean, we're here.
We never said we were going to return from Duna, so
You can't be disappointed. You set your expectations low.
This is Leica all over again.
Don't
go
there.
We're just
I mean, they sent her into space with no hope of bringing her back, so.
Well. Yeah.
Yeah.
Too soon, Rob. Too soon. It's always gonna be too soon for Leica wasn't space dandy, and that was great.
Tumbly.
He's going.
We meeting
It's like fucking